Hello. In this video, we're going to cover the first of 3 discrete probability distributions for Lab 7. So remember, discrete means a whole number value. So a discrete probability distribution just has a whole number of outcomes. So the first example, the first kind of distribution we're going to look at is the Bernoulli, which has 2 outcomes. One, we usually call it success, and 0 a failure. So 0 or 1 is the outcome of a Bernoulli trial. And so we could consider flipping a coin as an example of a Bernoulli trial. And so we could plot this. If the chances are 50-50 of getting a heads, calling that a success, or 50% for a tail, calling that a failure, we can plot this. So bar plot uses the 2 different values we're going to plot. Names argument is a new argument I'm going to use just to label the x-axis. I don't know why bar plot uses that, but y limit from 0 to 1 to make the probability maximum 1, and main is title. So that's just a refresher on what bar plots do. So there's our bar plot for a Bernoulli random variable, the event of flipping a coin. So where it gets interesting is when the probabilities are not 50-50. So let's look at an example here where there's an insurance company that found that 30% of the people they insure meet their deductible in a given year. The deductible is when you you end up paying enough that the insurance company starts paying more for your bills. So it's in the insurance company's best interest that people don't meet their deductible. So we're going to consider success where someone doesn't meet their deductible and a failure where a person does meet their deductible. And let's plot this distribution. Before I go into this, I'll recommend that you pause and try to do this on your own. As much of this lab as you can do on your own, you're going to learn more and solidify what you've already learned. But do remember, copy paste is your friend. So if you copy paste the previous example and modify it, we have to consider, okay, what is the probability of success? The first argument, success, corresponds to the first value. Success is when someone doesn't meet the deductible, so that would be 70%, 0.7. And failure is when someone does meet the deductible. So that's how we'd plot this, and let's just change the title here. It's still a Bernoulli random variable. 2 outcomes, that's all you need for a Bernoulli random variable. And we'll call this meeting a deductible. And you can plot that. You have your beautiful bar plot for the Bernoulli distribution. Okay, so one important idea with a Bernoulli distribution is if we look at many trials, many independent Bernoulli trials, independent meaning one trial does not affect another, we could look at what is called the sample proportion, which is, here's a math formula. Double dollar sign just means I'm giving you a math formula. So p hat is a sample proportion, and we add up all the outcomes, 0 or 1, and divide by n, and that gives us a proportion. This should look familiar. So let's do an example. Where we're going to use the sample function here. And I've opened up the help file for the sample function. And you can see the first argument, x, is the 2 different outcomes. We're going to sample from 0 and 1. And size is 10. And we've done this before. Another argument here, replace equals true, means after we've sampled something from our set, we're going to put it back in there. Because if we were to remove it, we'd run out of outcomes. When you have a big sample size, sometimes we don't want to replace items, but we're going to make sure that we're replacing. This means every time we sample from 0 and 1. That's what that means. And then the probabilities are no longer equal, so we have to specify those too. So the probability of failure is 0, and the probability of success, not meeting the deductible, is 1. And so Oh, this shouldn't be in there yet. I'm just going to run this. And this shows a sample of 10 people I picked. And 0 is failure, 1 is success. And if we want to find the sample proportion, we take the sum of those, we add up all the ones, and divide by the total number. And so let's run that now. Okay, so 0.6 is what the sample proportion is for this example. So see if you can do this for the next problem. Let's change it to 100 trials and see what the sample proportion is. So I'm going to copy paste here. Same drill, we're sampling from 0 and 1. Instead of 10, we're going to sample 100 now. And everything else remains the same. So if I run this, we got our 100 trials that we sampled from using a random number generator that the computer uses. And instead of dividing by 10, now we can divide by 100. And there's our sample proportions. Okay, so I'll let you do number 4 on your own. Last part of this section is a little bit of theory regarding the Bernoulli trial. It has mean and standard deviation that we can actually calculate using a little bit of theory, but I'm just going to give it to you here. So the groundwork is we got a Bernoulli trial X. It's got probability 1, probability of, ooh, they should read P here, of P for outcome 1, success, and probability of 1 minus P for 0. Okay, so I'll update that and that'll be what you get. So P is the probability of success, 1 minus P. Glad I'm going through this. 1 minus P is probability of failure. And notice if we add P and 1 minus P, what do we get? It's the total probability for all the outcomes, which is 1. And so theory says if we take the mean of this variable, the mean should be P. And the standard deviation is this, which we may or may not use. I haven't decided. Okay, so your job, now you have to use your brain. You're going to have to think, how does the previous problems we just solved show the law of large numbers? That's what I'll leave you with. We'll continue next video on the geometric distribution.